My name's John Fletcher. I'm the CEO and Chief Scientist at the Innovation Game. And this is an idea I had about 10 years ago, so it's been a long time coming. And it's finally all kind of out there in the wild, so we're ready to tell you about it. So this is the Innovation Game. So our mission at the Innovation Game is really, I guess, fourfold. Incentivize any person or thing which is capable of optimizing algorithms to do so, and really sort of concentrate these efforts on the challenges which are most important for humanity. And in so doing, we'll make algorithms an investable asset class for the first time. Hasn't really been investable before, for reasons I will explain. But crucially, we do all of this while keeping the innovation open, which is often something which is at variance with investability. But in our case, we found a way to do it. So it's important that the algorithms continue to benefit the many rather than the few, and aren't locked up in kind of proprietary property in companies or as secrets. So algorithms run the world. Truly, there are so many applications. It's just dazzling. Almost everything, really. MRI scanners, turning measurements of magnetic fields into images, designing new materials, designing proteins or folding proteins, neural networks you've probably heard quite a lot about lately. And all of this stuff is, algorithmic research tends to be open, or has historically been done in the academic context, which means that people publish it openly. And this is, really quite fortuitous, because the algorithms are more powerful really than any other factor in computing. So it's more powerful than hardware, it's more powerful than sort of data, although you tend to hear a lot more about people investing in hardware and data. Algorithms are more impactful. And we kind of have an example of this recently. You might have heard about the recent AI boom was triggered by an algorithm, the transformer architecture, rather than by, better hardware or more data that had been around for a while. But once they got this new way of training neural networks, a new algorithm, it led to this enormous leap. And yet, you don't hear about the algorithm so much. Sam Altman talks about investing $7 billion in new hardware. He doesn't talk about investing anything in algorithms, as far as I've heard, and that's for quite an interesting reason. So this is from quite a recent paper which studied the effect of algorithms. I think they looked at 110 different algorithm families, sort of important things with scientific and industrial applications. And they compared it to hardware. So this grey line is the hardware improvement. Note this is an exponential scale, so this really represents an enormous speed up due to hardware over the past, I guess, 40 or 50 years. These sort of red line and the blue line are just a couple of examples, representative examples of the 110 algorithms that they looked at. And you see they work in quite a curious way. So you can get just nothing for decades, and then suddenly sort of boom, an effective compute speed up which eclipses everything that you've got, cumulatively from hardware over the past 40 years, and then, maybe nothing for several decades. So this really explains why algorithm development isn't really the sort of thing they do in industry so much. It's so unpredictable, it's sporadic, it relies on human insight. And whereas you can just kind of, historically they've seen you can turn the handle and get better and better hardware improvements which apply to all types of computations. These types of computations, these algorithms will apply to a specific thing, and if this is your field and this is the algorithm that's important to you, you might not, you could probably invest billions in trying to find a better algorithm, just find nothing for years. So they really have historically left it to the academics. But what's happened when you look at at least the 110 different types of algorithms they studied in this paper, is that the total effect of the kind of equivalent speed up in compute that you got from algorithms was significantly more than you got from hardware, taken together. And in fact, hardware is plateauing because Moore's law is coming to an end, and the transistors are getting to the atomic scale. But as for algorithms, another interesting fact about algorithms is that they have more impact the larger the problem size you're attempting, whereas with hardware it's relatively independent of problem size. And what this means is that this sort of divergence between the impact of hardware and algorithms is set to increase even more in the future as we have larger problems in, big data, data-driven science and AI. So this is the way that things are going, and it shows, the kind of extreme results that you can get from algorithmic breakthroughs. So just to summarize, algorithmic innovation is currently, it's kind of slow. One of the reasons is that there aren't many people who can do it. It's done in academia, and one of the downsides of the academic world compared to industry is that resources tend to be allocated somewhat less efficiently. But a big upside is that academics tend to publish their work, and then sort of the algorithms are a sort of common factor between industry rather than being sort of owned and proprietary in one company. The transformer architectures are an interesting thing because it was openly published by Google, but it's generally believed that they might not do that again if they had something of that magnitude again. So development of algorithms it's currently very unpredictable, again, because of the sort of sporadic nature, reliance on human insight, and it means that that most of this happens in academia, inefficient funding models, but open. And the downside of making it investable would be that the proprietary nature of applied research, tends to push them to keep it closed, and this could lead to monopolies. And it's very extreme in the area of AI, as I'll explain a bit more in a minute, because you can have an algorithm which is improving itself. And in that case, you could get a sort of exponential takeoff, which could be quite sort of destabilizing and even dangerous. And interestingly, I thought this wasn't going to happen. I was thinking about this problem for a long time, and I thought that the age of automated algorithm development was still a way off. But in fact, it seems it's not the case. So in this relatively recent paper by Google DeepMind, they published it in Nature. They found sort of significant improvements in the state of the art and 3 types of algorithms using basically neural network, a kind of compute-intensive process for searching for algorithmic improvements. And this is sort of expensive, compute intensive, but the interesting thing about it is it's scalable. You might not have twice as many scientists who are capable of improving algorithms because they're really rather a scarce commodity, but it's relatively easy to buy twice as many GPUs. And that means that this process is scalable, but because you have to invest in it, you've got to put money into it, then the result that you get out is pretty difficult to make it sustainable if you don't then keep that algorithm proprietary. And this is kind of, we sort of know this in a slightly different context in AI. OpenAI decided they couldn't be competitive if they, made their work open because they couldn't afford to train the models, which is very expensive. And we've got more recent examples, things like Stable Diffusion, I think is sort of, going downhill. It's an open source sort of image generation model. But because they make everything open, they can't capture the value that they generate. So it's kind of an economic problem that we face. So the solution is the innovation game, which is the first and only protocol designed to accelerate algorithmic innovation, but keep it open. So any person can innovate on algorithms, or a thing, a computer, it could be an automated process. And when they find an improvement, they can sell it. There's a ready-made market there for them to sell their algorithmic advance and get a token reward in return. And the 2 key mechanisms this uses are price discovery, so something we call a synthetic market, which is driven by optimizable proof of work. We'll go into a bit more detail in a minute, but a lot of people have heard about proof of work in the context of Bitcoin. And it's kind of analogous because you might know that Bitcoin uses these special machines to kind of compute hash functions. And that means, suddenly if you could have a better machine to compute a hash function, 15 years ago that would have been worth nothing, now it could be worth billions. So it causes a market incentive, it's a source of demand for a thing which could have been arbitrary, really. It's something that they chose. It happened to be a SHA-256 function, but it could be any sort of function. And that's really the same process that we use. The benchmarkers, as we call them, who are like crypto miners, create a market for these algorithms. So the second strand is value capture through a hybrid licensing model. This is heavily inspired by open source. There are 2 options. One is an open license, it's the so-called open data license, which means that you have to share your data if you use the algorithm, the data that you processed. This is the kind of thing that will be agreeable to academics because they're supposed to give enough information so you could reproduce their results. We anticipate that many companies, they may not want to share their data, it's kind of their asset. So in that case, they've got a commercial license paid option, which sort of frees them of this obligation to share their data. But crucially, the revenue that's generated by this goes back into providing additional reward for more open innovation. So it's just looped back, and that's how you sort of justify giving the commercial people an option to buy themselves out of the obligation. So optimizable proof of work is a revolutionary type of proof of work mechanism, which I'll go into in a minute, but it uses multiple different sort of independent types of proof of work. So you have lots of different problems, things to do with, it could be kind of sensing, MRI machines, neural networks, protein folding. It's got a very sort of diverse range of problems that we can put in there. So it's not just one problem like Bitcoin or something like that. It's multiple of them, and they all have to be solved in parallel. And this ensures the security of the protocol. So I just wanted to quickly talk about, in case anybody had looked at the white paper, maths always seems so intimidating. But I just wanted to quickly point out that this is, in fact, extremely simple, well, as maths goes. This is really just a standard deviation. Some of you may have come across that before. And what that means is that, if you have a certain number of quantities, if they're all similar, the standard deviation is low. If one of them is sort of high and one of them is lower than the other, the standard deviation tends to be relatively high. So it's basically something which is small when all of these factors have a similar value. And this is just standard deviation divided by the mean, which is called coefficient of variation. And this just says that your rewards as a benchmarker are a sort of negative exponential of your coefficient of variation. So the further out of sync you are, you're doing one proof of work a lot more than another, and another one even less, you'll get fewer rewards. If you do all of them about the same amount, you maximize your rewards. And that's really just the essence of what's contained in these equations. So we have a sort of physical analogy over here, which is if you had one guy who was a super rower, is 100 times stronger and faster than the other rowers, of course it would be an advantage to your boat, but the advantage would be limited because, all the rowers have to row in sync, otherwise the oars will clash, right? So you couldn't have one guy rowing twice as fast as everybody else. So that's just the principle that the proofs of work sort of constrain one another in a sense, because if one is optimized a lot, it kind of is of limited benefit to the guy who optimizes it if he just keeps it to himself. And so the incentive is to upload it to the network, everybody upgrades, and he gets royalty or fee if other people use his algorithm. So that's the way that the incentives work for benchmarkers in the innovation game. So this optimizable proof of work then allows a massively expanded sort of set of problems to be used as proof of work. The problem before, where everybody believed that you couldn't have a proof of work of these types, is that if somebody found one of these algorithmic optimizations, you kind of saw it's like boom, there could be 100 times more efficient than everybody else. And if you're using it for this application, it just means you put all the other miners out of business, and it's no longer a decentralized protocol. So it simply doesn't work. You have to have this sort of constraining formula, which I just showed you. And that means that we can do all sorts of interesting things now. NP-compete problems like Boolean satisfiability. It's used in microchip design, for example, optimization problems. Convex optimization is used in machine learning. Scientific inverse problems like medical sensing, remote sensing. This is actually what I did for my PhD sensing problem, which is why I first had the idea. It's hard to solve, but easy to verify. So onto the licensing part. As I said, we're really inspired by open source. I didn't really know until relatively recently. Open source really is such a phenomenon of the last 25 years. It's in everything. Linux, for example, is in every smartphone, all Apple smartphones, all the Android smartphones, that's all just Linux. All of the Apple computers on most servers. And in its domain where it works well, it really sort of overwhelms proprietary alternatives. You have lots of people collaborating and building upon one another's work. Bugs are spotted quickly, you get things sort of faster and higher quality. So it's this amazing kind of success story of something which is not, it's a public good, it's not funded necessarily by anyone, although now, lately some big companies do contribute to it, but that isn't required. So, many people think, why can't just everything be open source? But it's interesting, all of these super successful projects, if you look into them, they have a particular type of structure. They tend to be large code bases, highly modular, so people can, contribute sometimes in their spare time on some widget without having to have a global overview of all the software. But not everything is like that. Algorithms are not like that. because algorithms, things like machine learning models are not like that. You need revenue to come in, otherwise you can't be competitive. And this is the reason why the AI companies, have many have gone proprietary, and the ones that haven't are going out of business. And it's one of the reasons you can open source anything you like, but it doesn't mean it's going to be a successful project. There are many open source algorithms, but there aren't people sort of piling in and improving them in this sort of massively collaborative way, like they do with sort of Linux and Apache Web Server and all these kind of things. It's because they have a different structure. And you need to capture some of the value that they generate, otherwise you can't be competitive. You really have to be a full-timer to have better algorithms. It's such a difficult thing to do, so you need to get paid. And most of the people who get paid to do it are academics currently. But so we looked at this problem, and we really, the kind of core of the issue was identified almost 25 years ago by a guy called Eric Raymond, who was a big open source pioneer. He saw that some types of software don't work if you can't capture the value, and crucially, route that value back to the people who contributed to the open source project, the open source contributors, in a sort of way which the value of their contribution is reflected, a sort of market determined mechanism. So there's no answer to this in general, but we have solved it for the special case of algorithms. So how the innovation game works. I mentioned this concept of a synthetic market here. You have benchmarkers who are essentially assessing the methods, because they're trying to sort of mine as many tokens as they can. If a better method, more efficient method comes along to do the mining, they're naturally going to adopt it. They don't want to sort of waste electricity or power. And so in the innovation game, the method that the benchmarkers are using is simply defined as the best method, the one that deserves to get the reward. The methods are contributed, methods being algorithms by the innovators, and then we capture the intellectual property, copyright and patents. It's held in the TIG Foundation, and it's available for license. Not just to commercial enterprise, but really we foresee that they'll get a commercial license, a paid commercial license, but they could choose to take the IP under the open data license, which includes the data sharing obligation. So that's really where the demand from the token, for the token comes from. It's kind of a closed system. It sort of loops back in a market determined way. So just to summarize, the block rewards are divided between innovators and benchmarkers. Innovators sort of assign their IP over. It's sort of similar to the open source project. You have to give a license to a patent if you had one of the open source projects, and it's the same for us. Or if they don't already have a patent, we ask for the right to file one. But all of this is made available under an open data license, as we said. And this means that we can take algorithms from a very diverse range of fields, because everything is crowdsourced. Even the largest companies, they're not going to be working on typically MRI scanners as well as neural networks, as well as folding proteins and mechanical problems and all this sort of stuff. But an open protocol can have a far more diverse range of interests than any company could. And because of the diversification, that makes algorithms sort of investable, because it's the classic thing. Any one algorithm is a very uncertain proposition, but taken together as a sort of portfolio, it can be investable. So the market opportunity, well, this is kind of more for the VCs, but the addressable market, really would go into the trillions of dollars. AI microchip design, I don't think that's hard to imagine. And efficiency gains from new capabilities. It's not just making current things faster. You can have entirely new capabilities, sort of things made possible when you get algorithmic breakthroughs. It has the potential to become the sort of leading way that people develop algorithms. The peril at the moment is that if private companies, or certain, just a very small number of private companies with access to compute, start developing algorithms in a sort of systematic, compute-intensive way, then as an academic, they always want to be working on the best thing, right? So if they don't have access or sight of the best algorithms in academia, they're going to go and work for the company with the most compute. And this has sort of happened with open source, that you can't really play around with the world's best, large language models, for example, unless you work for Google, because they're not open source. So this has a danger of perhaps, it could happen for algorithms too. Oh yeah, and it's more efficient resource allocation than a nation state because nation states fund these things because they can capture the value, but they don't distribute resources on a market basis typically. So the vision of the future, sort of what does all this add up to? Well, we imagine that people, human beings, will still be involved in algorithm development for a while. Maybe sort of in collaboration with machines, you'll get a better algorithm out from the machine, and the people can sort of maybe tweak it and refine it even further. And this will accelerate the pace of algorithm development, no doubt. But it's crucial to find an economic model, something which makes sense while keeping the research open. And if this is done, I mean, it'll be even better. The research will be fast because people can build upon one another's work, and they can also sort of afford. The academics have sight of the best stuff because the best algorithms are open, guaranteed. Go to market. So this is really just kind of supply and demand side. Skip over this quite quickly. Benchmarkers provide demand for better algorithms because they simply want to earn tokens more quickly. And innovators, of course, provide these algorithms. So then you have these so-called curators. We want people to suggest challenges for the innovation game. We just have 3 challenges in at the beginning. If you have too many challenges in the beginning, the reward for each one is a little bit too small, so they have to sort of grow as the value of the protocol itself grows. And also, we want to get ones in which are genuinely useful in industry and science. And the demand side comes from, many people are monetize algorithms, people like MathWorks, they have them in, I think it's MATLAB. Industries, pharmaceuticals, AI, of course, and crypto companies also, everybody has a demand for algorithms. So just quickly on the team, my name's John Fletcher. I have a PhD in maths and theoretical physics here at Cambridge. I looked at, sensing a fractal dimension of a fractal surface by scattering light from it. It's kind of a sensing problem. Our CTO, Ying, unfortunately can't be here tonight. We kind of went into business together about 5 years ago. His background is in AI and also sort of blockchain related. Philip David, who did most of our licensing work, he was formerly head of legal, general counsel at Arm Holdings, intellectual property expert, and Lee Hughes, he was had his own derivatives company in the city, so he handles the commercial side. So as for our roadmap, phase 1, benchmarkers, innovator onboarding, that's what we're doing right now and have been doing for about 5 months. In phase 2, there'll be locked deposits, which makes things a little bit more secure. So the benchmarkers are required to hold a certain size of deposit. And then we're sort of really just trying to expand the challenges. That's the main the work to be done, getting more challenges in the game, and then putting the thing on the blockchain for full decentralization with optimizable proof of work using the consensus mechanism, which is a bit of a technical thing. We can ask me about that later if you're interested. That's it.